Professor Devoret, the F.W. F.W. Benicky Professor of Applied Physics at Yale University, Professor Collège de France, John Bell Prize, Europhysics Adjunct Prize, American Academy of Arts and Sciences, Descartes, Huygens Prize, Ampere Prize, Fritz London Prize, and member of the French Academy of Sciences. Professor Devoret is going to tell us about protecting quantum information in superconducting circuits.
Okay. Do you hear me? Okay. I would like to start by thanking Bill for inviting me to this Kavli session of the March meeting. And I'm going to talk in this last presentation about the fascinating subject of protecting quantum information. This has been already discussed by the previous speakers, but I would like to focus on this question in the realm of superconducting circuits and basically take on where Andrew Cleland has left his talk. So I'm going to present actually a brand new data at the end of this talk, and I would like to point out the names of Shantanu, Stephen, and Alexander who have worked on the experiment. My talk will not go in, it will be just an introduction to the subject that I want to cover, and I would like to invite you to attend this talk tomorrow, in particular, the talk of Rob Scholkopf, who's listed here as one of the PIs, and who will explain in detail our plans for protecting quantum information in an efficient manner, in a hardware-efficient manner. Okay, so when discussing protecting quantum information, I think it's a good thing to start by discussing classical information and the relatively straightforward way in which we protect it. So here, I'm going to consider basically the work memory that you have in your laptop. It's made of switches, and here I'm caricaturing these switches by using a trivial mechanical switch. The way you protect information encoded in this way is that you make a very high energy barrier between the state 0 and 1. And by imposing friction on the system, and basically by making sure that the energy barrier is much larger than quantum fluctuation, thermal fluctuation, you have an exponential suppression of the error rate. And this is basically the technique that is the primary level of protection of classical information. Quantum information is much harder to protect. You have two states, 0 and 1, but you have also all superpositions, which are represented by this Bloch sphere. And so there's no question of now of using dissipation, because among all these states, there are states that are going from 0 to 1, and friction would kill these states. There is also something that prevents you from using dissipation, is that you want to make operation on this qubit, and these operations have to be reversible. And dissipation is going to kill this irreversibility, or basically the environment is going to observe the qubit while you are modifying it. So in discussing the protection of information, it's interesting, it's a convenient to, instead of talking about the whole Bloch sphere that you want to preserve, you can actually focus on only 6 states. Basically, the skeleton of the Bloch sphere, which are obtained by adding to the 0 and 1 state, which are eigenstates of the Z operator, the poly Z operator. the eigenstates of the x and y operators, which are orthogonal to the z operator. So we have this octahedron, and this octahedron represents the quantum information. If it is harmed by the environment, let's say in a T1 process, the octahedron shrinks, and as you see, there are different ways in which the octahedron can shrink. And in general, there are three independent error processes that we have to fight, instead of one, as in the classical case. Now, Duncan, in his talk, explained that symmetry was a way to protect quantum information. So if you have, let's say, an m equals 0 state, where m is the projection of angular momentum along z, this state will be robust to magnetic field components along the x and y component. And basically, we are protected from a common mode magnetic field here. Of course, we're not protected against all perturbation, but this gives an example of a kind of elementary protection of quantum information. In general, the recipe that we know is that you have to encode your quantum information in a large enough Hilbert space and in a clever entangled state like this one, in such a way that any error will live in a direction which is outside this tri-dimension x, y, z. So it will occur in a fourth or fifth or sixth dimension, and basically the noise will not contract the octahedron. It will simply move it bodily so that we can recover the information in it. So this is, of course, a general recipe, but how do we get there? So there are actually three strategies, and they've basically, the first two have been already discussed by my colleagues. And of course, the first one was discussed at length by Duncan and Cam, and also by Dale. And they are based on encoding quantum information using defects in topological quantum matter. That's a very far-reaching idea, extremely ambitious, but we still need to get a way to control these, for instance, these defects, for instance, Majorana fermions. So this is a very long-term idea. This is basically the program of condensed matter physics for the next 50 years. And it's a very important domain. There is the other method that was mentioned by Andrew, which is to use a register of qubits. And then monitor the multi-qubit parities of this register. So this idea, which is derived from the STEANE code and which is generalized in the surface code, as Andrew mentioned, has some link with the use of topological quantum matter. And in the next slide, I'll give you a very short introduction to this idea. But what I want to do in the rest of my talk is really tell you about a brand new idea, which is which we call hardware efficient, in which a minimal amount of hardware is used to correct quantum information. So just to remind you what actually is quantum error correction or information protection in a register of qubit, let's consider for a few minutes the basic idea, which is the STEANE code. The STEANE code encodes a qubit, a 0 logical and a 1 logical, using 7 qubits, each of which are represented by these hexagons here. And you see, you may already see that there is a deep symmetry in the way the entangled states of these qubits are created. So if you take this dashed line, you see they constitute plaquettes, 3 plaquettes spanning the 7 qubits. And if you look carefully around these plaquettes, you will see that there are always an even number of 1s or 0. So that's one symmetry. The other symmetry that you can see is that in the 0 state, you have either 4 1s or 0 1s. And for the 1 state, it's basically the opposite. You exchange the 0 and the 1. So by having these deep symmetries, you can actually protect this logical qubit from any external field that will create noise on each of these qubits. Since there are 3 directions for the field, there are 21 error syndromes that you have to detect. And this is done by monitoring the parities, the 4-way parities of these plaquettes here, which means you have to do constantly 6 multi-qubit parity measurements. And this explains basically why Andrew told us that you needed so many qubits to encode 1 logical qubit with this method. So at Yale, we have developed a completely different paradigm, which is based on a superconducting cavity. So instead of encoding quantum information in a transmont qubit or another qubit based on Josephson junction, we're going to encode the information in a superconducting cavity. Superconducting cavities are already very good. And here I'm representing it by the same kind of LC oscillator that Andrew has mentioned. The rate at which photons leave the cavities is extremely small. You know, it's the quality factor of these cavities is more than exceeds 1 million and attains 1 billion. And of course, we choose its frequency so that it is much larger than h bar omega 0 is much larger than thermal fluctuation, so that we can reach basically simply the ground state by letting all the excitation out. So these cavities can be driven by signals. And let me remind you that a cavity has various types of excited states. All these states I represent by their Wigner function, which is basically a quasi-probability in phase space. I and Q are the in-phase and quadrature component of the oscillator. But you can also think of it as the current in the inductance and the charge of the capacitor in the previous view graph. And this phase space is such that the ground state, the quantum ground state, is a fuzzy disk centered at the origin. Now, when you drive the cavity with an external field, the only thing that you can do is actually create a coherent state. Basically, it's a displaced vacuum, and this corresponds to basically the pendulum oscillating classically. There's a fuzz of the pendulum, but this is why it's called, these coherent states are also called semi-classical state. If you add a little bit of nonlinearity to the cavity, you can get these more interesting states. So you can get the 1 photon state, which is represented by red annulus here, and inside you have a negative quasi-probability. Or you can have this so-called Gaussian state, which is the squeezing of the vacuum. But actually, we're not going to use this commonly employed state in quantum optics. What we're going to use to encode quantum information are those so-called cat states, which are formed by superposing a coherent state and its parity conjugate, which is the state with the opposite phase. So when you do this superposition, you see in this Wigner function appearing these fringes here, which you can understand in the following way. What you have done is created a pendulum in which you have two essentially superposition of the blob going one way and the blob going the other way with a 180 phase shift. And when the two versions of the blob hit the bottom, you see they interfere, and this is how you can think of these fringes here. So these cat states have an interesting property. They have parity. So the cat state with the plus here is a state of even parity of photon number. It consists of a superposition of different Fock states, but with even numbers. You can actually go to the odd cat state, which has a minus sign here, and if you observe closely, instead of a red fringe in the middle here, the odd cat state has a blue fringe. It has a negative fringe in the middle. In fact, you can show, this is a property of the Wigner function, the spot in the middle here, red means that you have an even state, and if you have blue, it means that your state contains an odd number of photons. We can use this coherence, these cat states, the property of these cat states to encode information in an efficient way. And let me explain how it works. So for instance, one method that we have used, and I'll talk more about this, we can encode information in the superposition of two even cat states. So we can take a cat like this, which is horizontal and which is even. Look at the red fringe in the middle. Or we can take this one, which is simply dephased by pi over 2. And this combination, this manifold, you can think of it as using a manifold of excited state of the oscillator, has very interesting properties, which are not without relation with actually the type of ideas that have been put forward with Majorana fermions. You can think of these blobs as sort of excitations. Okay, so what happens if you, for instance, wait and the cavity relaxes? It will actually, this is what will happen to the cats. So there will be a loss of energy, which shrinks the distance between the two blobs, as here, but that doesn't really harm the information. That actually, for a while, your information, which is encoded in these fringes here, is preserved. At the same time, when you lose a photon, during this typical evolution time, there is a phase shift that's occurring, because you see, you go from even to odd parity, and this odd parity imposes a phase factor here on this bottom state. So there is a shift associated with a photon loss, which you have to detect. So you have to measure, as time goes on, the parity, but the parity is changing in the manner of a classical bit, in a way. You have one channel of random errors to detect. The shrinking of the cat is a continuous process, which you can undo by a process which we call cat pumping, which is somewhat a cruel term, but which describes really what happens, as you will see in a minute. So this is the problem. We have this resonator, we encode information in it, but how do we control the information? Remember, if we just drive the oscillator, and we have no nonlinearity in it, we just displace everything. So we need to do something more. And you can do more by the following technique. So we're going to encode information in this left cavity here. This is what we call the storage cavity. And the storage cavity is going to talk to this other bigger cavity, which has a hole in the back here. And that's an entropy dump. This cavity is going to take out the entropy that's created when we correct the error of the storage. And in between the two, we have this superconducting qubit, this transmon qubit, which Andrew has described, and with which is just a simple Josephson junction with a capacitance across it. And in the back here, we have a quantum limited amplifier whose chip is based on the Josephson ring modulator represented here. So basically what we are really doing here is creating a Maxwell demon. This is the whole subject of protecting quantum information is actually an interesting game, which is inventing a demon that corrects the error due to decoherence. So in a nutshell, here are the degrees of freedom that we are using. We have the storage, and this is only one mode of the cavity that we are using, this T mode here. It talks to a junction that's a bridge between the two cavities. So that's the junction is an anharmonic oscillator. And then we have another harmonic oscillator, which is well open to the outside. And this is the Hamiltonian. So we have basically three modes with 3 frequencies here. And the junction is the dominant nonlinear one. You see this Kerr term here. And there are now two very important terms that you have to consider. So this term couples the number of photon in the storage to the number of excitation in the junction. So we can use the junction to read out the resonator and the storage. And then we can read out using this right resonator, we can read out the qubit by the well-known technique of circuit QED. Here, I'm going to use another term, which is this one. This is the last fourth-order term, which is going to be very precious. If you look at it, you see it destroys, it is able to destroy 2 photons in the storage and create 2 photons in the dump here. So what this is going to create is a force, actually, which is proportional not to the position, but to the square of the position. And also, we're going to use this term to create a loss. But the loss is not going to be proportional to velocity. It's going to be proportional to the square of the velocity. So you see, by coupling to the square of the position, or to the square of the velocity, we influence the states of the resonator in a manner that preserves parity. And that's this whole idea of using symmetry to protect information. So how do we prevent the cat from shrinking? After all, the cavity is open to the outside, it has losses, the cat loses its energy, so we have to repump it. And so this is precisely done with this 2-photon drive and dissipation. The junction is a mixer. It takes 1 photon of the dump here, or the drive, and then combining it with the pump, whose frequency is carefully chosen, it will create 2 photons in the storage. So you see, this is a drive that is a 2-photon drive, or drive proportional to the square of position. Here, we have the reverse process, which creates losses. And the combination of the two creates in phase space 2 minima here, which are explored by this experiment, in which we start from a state in the phase plane, and we see in which corner, in which of these 2 states it falls. And this has allowed us to map this diagram, which is actually fully symmetric. It is when you drive an oscillator, these dynamic states is completely parity symmetric. And with these techniques, we've been able to have a cat jump out of a vacuum. This is applying this two-photon drive. At first, it squeezes the state, but you can see this small mustache of the cat appearing. Of course, this was a preliminary experiment. We did not have a very good relationship. We had a ratio of 1 between the two-photon dissipation and the one-photon dissipation, so this was not very spectacular. In this new architecture, where we separate the qubit that does the Wigner from the qubit that does the mixing, we can get much better cats. And there is a spectacular experiment which we have been able to do recently with this much better parameter, is actually to be able to do a Rabi oscillation of this protected cat. So the cat is protected, it is pumped, but you see not only you can witness the fringes which show that you have coherence, but you can manipulate this coherence by a sort of drive. In this case, it's an example of quantum xenodynamics. It's dynamics of a quantum system which is continuously protected. And so the diagram on the left tells you in the cat space here what trajectory you're doing for this cat qubit. Now, I am running at the end of my time. I'm going to just flash very quickly these transparencies which show that we can do a pi over 2 Xeno gate in 1.8 microsecond, and go also very quickly over this last topic, which is the fact that we can actually correct for the photon number parity jumping. So this is an experiment done in the group of Rob Scholkopf, with which we have this long-standing collaboration. And basically, the set of experiments which Rob will describe tomorrow in a nutshell are the following. So if we encode quantum information in a transmon without any protection, we get a rapid decay. And basically, after 100 microseconds, there is essentially no information left. You see the octahedron has shrunk completely. Now, we can encode the information in the cavity coupled to the transmon, but not perform any error correction. And since the cavity is much better, we can actually get a longer lifetime. But that actually shows that it is better to encode information in a superconducting resonator than a transmon. What is spectacular here in this experiment is that you can actually monitor the parity and actually correct the errors. And in this experiment, a break-even was obtained, meaning that not only you get a better fidelity that if you don't correct, but you can get a slightly better fidelity for the information than the best way of encoding information, which in that case is simply a superposition of 0 and 1 photon. Okay, so this is my summary. So we have this new method of CAD codes to efficiently protect information. So I didn't talk about it, but this information storage can also lead to gates and to entanglement. And we believe that this is a very promising implementation of quantum protection, and we hope to demonstrate with this architecture different hierarchical layers of fault tolerance. Okay, and I will end up by thanking you for your attention.
Thank you very much, Michel. Are there some questions?
Thank you very much for your talk. Professor Cleland showed that for large quantum computations you'll need a large number of qubits, millions even. How do you consider that in relationship with the large size of these resonators?
So with the resonators, we think that we could essentially replace something like 100 qubit of the surface codes by just a few cavities and a few transmon. So the way to think about this economy is the following. So you know, when you read a book on quantum information, it is explained that you should never use the states of the hydrogen atom to encode the information. Why? Because even though there are an infinite number of states, in fact, they are very hard to manipulate in the sense of doing operation. But actually, they are great for protecting information. The fact that you cannot manipulate the state is a good sign. It means that there are symmetries in the hydrogen atom that actually prevent the population from going everywhere in the state. So this is basically what our approach is based on. You want to use an harmonic oscillator because there are very powerful symmetries in an harmonic oscillator which prevent the coupling of your information to all kinds of noise. And that's what we're using. That's where the economy comes from.
If I could just follow up, but your systems are very large, so even if you save a factor of 100, will you be able to put enough of them together to build a useful device?
Yes, so yes, so the cavities that we are, first of all, the cavities that we are using, so I didn't put, that was a mistake, I should have put a scale here. This is actually a few millimeters across. So this is actually still a very small system. You could put thousands of them in a big dilution refrigerator. But there are also, and that's work done in Rob's group, where you can miniaturize a cavity. A cavity doesn't have to be to have a large volume. It can be microfabricated with flip chip techniques, for instance. So you can have actually a small, high-quality resonator, which is, in a sense, which has 3D vacuum inside.
Another question?
So how do you intend to have many qubits inside of your cavity, say 15 qubits? Because the larger the photon level, the faster the relaxation rate.
So yes, so that's what you're alluding to. The fact is that I'm using of order 15, 20 states in my oscillator to make a cat state. That's very true, and it's true that when you consider higher level Fock states, they relax faster than the one below. In fact, the relaxation rate increases as n. But if you think about a register, let's say if you have 7 qubits, well, the rate at which an error happens is 7 times what an error would happen for 1 qubit. So the situation is a little bit worse for the cavity, but not so worse than a register of qubits. In fact, if you use 2 cavities instead of 1, you can show that the situation is very favorable.
No other questions? I'd like to wrap up this wonderful session supported by the Kavli Foundation and give thanks to them and all the speakers that we've had this afternoon.